Since the force is constantly varying, we need to use calculus, specifically integration. So here's the general form. Work is the integral from an initial position to a final position of the force, dx. We want to calculate the work done by the spring. There's our subscript. And we're going to go from x equals 0 to x equals x. Then we substitute. And again, we use the force of the spring, not an external force, so that gives us a negative. You integrate x squared dx, you get x squared cubed over 3. You evaluate it between the limits x and 0, and here is the work done by the spring. Now, how do we calculate the potential energy for this system? And here's what we have from the previous slide. And the way we could calculate the potential energy, that will be the negative of the work done by the field, or in this case, the spring. So UE, elastic potential energy, is negative the work done by the spring, and that just cancels out the negative sign, and we get 1/3 kx cubed. And remember, for a linear spring, we got 1/2 kx squared. The potential energy is positive. That means that work done by the external force, you pushing it or expanding it, will increase the potential energy of the spring mass system. Now we're going to go into the other direction. We will find the force from the potential energy. When we have the potential energy for a given system, we can calculate the force on an object that enters the region where the potential energy is working. We derived the potential energy for conservative force earlier, where the subscript F, and that's right over here, indicates the work done by the field, such as the gravitational field or the work done by a stretched compressed spring, as the object moves from an initial x position to a final. So the potential energy is a negative of the work done by the spring, and that's where this negative comes in, and then we integrate the force over the displacement. We will now take the derivative of both sides of this equation, the derivative of this piece and the derivative of this piece, and we'll get du dx. And then over here we have d by dx of the integral, and these guys just cancel out. Again, math teachers would be far more rigorous than me, but I just want the answer. And we'll find du dx is minus f of x. So given a potential energy, we can find the force acting on objects that wander into its field.